So let's solve this hard problem. So suppose f of x is some function that represents the number of zeros at the end of x factorial. So for instance, f of 3 would be 0 because, right, 3 factorial is 6 and it has no zeros at the end, whereas 11 factorial has 2 zeros at the end, which is why the function returns 2. So now we're given some integer k, and we kind of want to see for how many values of x will it have k zeros at the end. So if you look at this example, you want zeros at the end. So this only happens for these numbers right here, right? This one goes up to 24. If you go up to 5 factorial, well, you'll have a 0 at the end, so therefore it wouldn't work because you have the function returning 1. So if we look at this example, though, we want 5 zeros at the end. And in fact, if you write out the list of all the factorials, you'll realize that it kind of skips having 5 zeros at the end. So you'll have numbers with 4 zeros at the end, and then you'll suddenly jump to having 6 zeros. So you won't actually have any 5 zeros in the middle, which is why we actually return 0. So there's a couple of tricks to solving this problem, and the first one is you kind of realize that the number of zeros that a number has at its end depends on the number of factors of 10 it has. Also, the number of factors of 10 that a number has depends on the number of factors of 2 it has and the number of factors of 5 it has. And sort of the number of factors of 10 would sort of be the minimum between A and B. Another thing to note is that the number of factors of 2 will always dominate the number of factors of 3. And it's simply because there's more multiples of 2 in a number than multiples of 5. So we actually don't have to consider the number of factors of 2. Let's just consider the number of factors of 5, right? Because it'll always be smaller. So in this case, the number of zeros at the end of any number depends on the number of factors of 5 it has. So now with that observation, you can kind of solve this problem. So another thing that you sort of want to note is that the output is only going to be one of two things. In this case, you're outputting 5 and you're outputting 0. There's actually no other possible output other than these two. And the reason why is that if you have a number, let's say if k was like 8, if you have numbers with 8 zeros at the end, you're going to for sure have 5 numbers with 8 zeros at the end. And the reason why is because let's say we have 5 consecutive numbers, right? A, B, C, D, E. Let's say this one previously had, let's say, 7 zeros. And then let's say this one gained a factor of 5, right? Let's say this was like 29 factorial. Now this is 30 factorial, so it gained a factor of 5. So therefore you have one more 0. So you'll have 8 zeros for A. Similarly, you'll have 8 zeros for this one because you haven't gained a factor by multiplying by 31. Similar here, you'll have, I think, 30, 31, 32, 33, yeah, 34. So you won't have another factor of 5, so you'll still have 8 zeros. And then when you get to 35 factorial, you're going to add another 0. So now you have 9 zeros. But in this case, you can see that because any interval of 5 must have a factor of 5, that sort of means that you can have at most 5 numbers with however many zeros in that sequence. So now that we know that the output can only be either 0 or 5, we can look at one last thing. And the last trick is that the constraints for this problem range k from 0 all the way to something up to 10 to the 9. And if you recall, having a solution with this runtime will actually result in a TLE, which is sort of why you have to think of either a O of 1 solution, which typically involves some crazy math, or some logarithmic solution, which typically involves binary search. So in this case, you can actually think of this problem as a binary search problem. So how can we binary search? Well, why don't we sort of implement a left and a right counter and then calculate some random mid value, check if the number of zeros of this mid value has k zeros at the end, and if it does, that means that there is some valid solutions. And in this case, we know from our previous trick that if there is valid solutions, then it must have 5 exactly. So in this case, what should we really set our right pointer to? Because we want to make sure that our factorial has something greater than or equal to k zeros. We talked before that the number of zeros kind of happens every fifth cycle, right? So like 5 factorial would have 1 0, 10 factorial would have 2 zeros at the end because you're adding on a factor of 5. So typically you would think it's somewhere around 5 to the k, but to be safe because of rounding, if you set it to 6 times k, it'll be fine. So now that you have your left and right pointers, you can sort of just binary search for some random mid values until you check, well, has the left pointer exceeded the right pointer, which in that case you have no solutions and you return 0, or if you see that there are a valid solution, you'll just return 5, and that's the entire trick. Okay, so let's start off by creating a function called zeros that takes in some integer n and returns the number of zeros at the end, aka the number of factors of 5. So for instance, if our n was equal to 34, well, how many factors of 5 does it have? Well, how many factors of 5 does this have? It has 6. But something else you have to note is that how many factors of 25 does it have? It has 1 factor of 25. So you actually have to kind of include this, right? Because this kind of contributes twice as much. So in the end, we're just going to return 6 plus 1. So that means this has 7 factors of 5. So how can we write this function? Well, we want to first calculate the number of factors of 5 it has. So in this case, we'll first check that. Also, we'll continue going while start is less than or equal to n, right? Because we don't want to check, well, how many factors does it have? A factor of 125? Well, this is clearly bigger than our n, which is 34, so there's no point in checking that. So while start is less than or equal to n, what we'll say is we need some res counter to return at the end. So our res is going to add on. How did we get 6 factors of 5? Well, it's just taking this number and dividing it by 5. So it just added n double divide by the starts. And then now that's how many factors of 5 we got. Now we have to check how many factors of 25 it has. So let's increment our start by a factor of 5. And that's all the code right there. So we'll return our res. Now getting into the binary search part, remember we have to initialize our left and right pointers to 0 and I believe 6 times k. So now while left is less than or equal to right, we'll calculate our mid value. And now we want to check, well, is the number of zeros of this value equal to k? If so, there are valid solutions, so we'll simply return 5. Otherwise, if the zeros of mid is greater than k, that means we have too much. So we have to shorten our window. Otherwise, we'll increment our window. And in the case that you have no possible solutions, left overrides right, then we can simply return 0. And that is in the entire code. And as you can see, it works perfectly fine.